Welcome to the deep dive. Today, we're jumping straight into chapter 32 of the Feynman lectures on physics. We're tackling radiation damping and light scattering. You're working through college physics. You'll know this stuff connects some pretty big ideas. Conservation of energy, electromagnetism, to things you see all the time, like why is the sky blue? We're aiming to unpack Feynman's approach, focusing on the intuition, not just formulas.
Yeah, and what's great about this chapter is how it kicks off with something almost, well, counterintuitive. You have a charge oscillating, it radiates energy. Okay, fine. But conservation of energy insists that energy has to come from somewhere. That forces you right at the start to think about how the system doing the driving actually feels that energy loss.
Okay, let's unpack that. Concept one, radiation resistance. So imagine you've got this perfect antenna, no normal resistance at all. You make it oscillate. It sends out radio waves, right? Energy's leaving. So where's the drag? Something must be resisting the driving force, otherwise energy isn't conserved.
Exactly. And that's radiation resistance. It's not heat loss in wires.
Right.
It's the circuit having to push against the very act of radiating.
Yeah.
The antenna acts as if it has resistance because it's constantly losing energy to the radiated field.
And this leads to a really deep question Feynman gets right into. How does the radiation actually push back on the charge to slow it down?
The little ball problem.
Yeah.
It's tricky. I mean, classically, how does a charge's own field exert a force back on itself? The field has to travel, right? So there's a delay.
The retardation.
Right. The field created a moment ago acts on the charge now. And calculating that self-force precisely for a point charge, well, it's notoriously difficult in pure classical theory. It kind of hints at the limits we run into.
But it sets the stage. We know energy is lost, so let's quantify it. Section 32.2, the rate of radiation of energy.
Okay, so how much energy? How fast? The key result here, the Larmor formula essentially, is that the power radiated, P, depends on the acceleration squared.
Not velocity, but acceleration.
Exactly. The change in velocity is what generates the radiation field that carries energy away permanently.
And Feynman walks us through visualizing this. You have the charge accelerating. Its electric field has a component that depends on that acceleration, but viewed from far away, it depends on the acceleration it had earlier.
Because of the light travel time, the retarded acceleration.
Right. And the power flow per area, the flux S, goes like the square of that electric field, Langle E2.
But you have to figure out the total power. You sum up, integrate that flux over a giant sphere around the charge.
And it's not uniform, is it? The geometry matters.
Definitely. If the charge accelerates up and down, say, along the z-axis, the power radiated depends on the angle to theta from that axis. It goes like a centi-theta.
Meaning no radiation straight ahead or straight behind.
Correct. Zero along the axis of acceleration.
And maximum radiation sideways, perpendicular to the acceleration, like a donut shape.
The classic dipole radiation pattern. And when you integrate that theta pattern over the whole sphere, you get the total power. It comes out proportional to 2 heavy 2, and importantly, the total power radiated doesn't depend on how far away you measure it. The energy just flows outwards.
Okay, so T dollar is proportional to A dollars, with constants like 100 C dollar pi epsilon C3. Assignment notes, sometimes you see A cutoff 4 pi epsilon dollar in older texts, just different ways of grouping constants.
Right, just notation. The physics is the atal to dependence.
So now, section 3. Radiation damping. What does this energy loss mean for, say, an electron oscillating in an atom? Even with zero friction, it should slow down, right?
It'd have to. It's losing energy by radiating. That slowing down is radiation damping. It's like an intrinsic friction caused by the radiation itself.
And we can quantify how quickly it decays using the quality factor Q.
Yeah, Q is a really useful concept for any oscillator. It's basically a ratio.
Yeah.
How much energy is stored in the oscillation compared to how much is lost per cycle, or technically per radian.
So high Q means?
High Q means it rings for a long time. Very little damping. Low Q means it dies out quickly.
And the example given is an electron in a sodium atom oscillating at optical frequencies. The Q comes out enormous, like $5 times 170 setters.
Huge, yeah. Which tells you two things. First, the damping effect, that effective resistance, gamma, is incredibly small for an atom.
I think second.
Second, that translates into a lifetime. How long does it take for the oscillation energy to drop significantly? For sodium, it's about 10 seconds.
10 nanoseconds. Seems fast.
Well, yes and no. For us, it's incredibly fast. But for an electron oscillating billions of times per second, 10 seconds is actually millions of oscillations. So it rings for quite a while in atomic terms before radiating away its energy.
Okay, that short lifetime, 10 seconds, is crucial for the next bit, right? Section 4, independent sources.
Absolutely crucial, because light is a wave. If you have two wave sources, math call, and dig2, their amplitudes add, and the intensity should show interference. There should be that 2 math call 2 term.
So, why don't we see interference patterns from two ordinary light bulbs? If you turn on two lamps, the room just gets brighter. You add the intensities. Why?
It comes down to that $10 second lifetime. An atom radiates a little wave train, then stops or gets bumped, then maybe radiates again with a totally random starting phase.
Ah, so the different atoms in one light bulb or between two light bulbs are completely out of sync.
Totally independent. The phase difference, 5200 net theta 2, between the light waves arriving from any two different atoms is jumping around randomly billions of times per second.
And our eyes, or any detector, average over way longer timescales than that. Milliseconds, maybe?
Exactly. So that rapidly fluctuating cosine term, sometimes positive, sometimes negative, just averages out perfectly to zero over any realistic measurement time.
Leaving
Just the sum of the individual intensities. Math call 12 plus math call 22.2. That's why ordinary light sources are incoherent. The independence of the atomic emitters washes out the interference.
Amazing. So the damping gives the lifetime ensures independence, and independence kills the interference for everyday light.
You got it. It all connects.
Okay, now for the grand finale. Section 5. Scattering of light. Applying all this to explain why the sky is blue.
Right. So sunlight comes into the atmosphere. It's
Yeah.
an electromagnetic wave, an oscillating electric field.
Hmm.
What does it do to the electrons in the air molecules, like nitrogen and oxygen?
It makes them oscillate.
And if they're oscillating,
We're accelerating.
bingo. And accelerating charges radiate.
So that air molecules absorb the sunlight and then re-radiate it in all directions.
Pretty much. They act like tiny antennas
Yeah.
driven by the incoming light wave, and they scatter that light.
And Feynman introduces the idea of a scattering cross-section, sigma dollar. It's not a physical size, right? It's like an effective area for scattering.
Exactly. It's the total power scattered divided by the intensity, or power per area, of the incoming light. It tells you how effectively the atom intercepts and re-radiates the light.
And the calculation, this is the key part, shows the scattered power depends really strongly on the frequency of the light.
Dramatically so.
Yeah.
This is Rayleigh scattering. The total scattered power turns out to be proportional to the frequency to the fourth power, omega 404.
Omega to the fourth. So higher frequency means much, much more scattering.
Way more. Blue light has roughly twice the frequency of red light, so 2 to the fourth power.
16.
About 16 times more scattering for blue light than red light. Violet scatters even more, but our eyes aren't as sensitive to violet, and there's less violet in the sun's spectrum to begin with.
So the blue light from the sun gets bounced around all over the atmosphere by these air molecules,
Scattered in every direction.
while the red and yellow light mostly punches straight through. So when you look up away from the sun, you see that scattered blue light coming at you from everywhere.
That's the blue sky. It's a direct consequence of accelerating electrons radiating without omega 444 frequency dependence.
And one last detail: polarization. Scattering polarizes the light.
Right, because the electrons are forced to oscillate by the incoming light's electric field. If you look at the sky 90 degrees away from the sun,
Perpendicular to the incoming sunlight.
the electrons are oscillating roughly perpendicular to your line of sight. They can't radiate along their axis of oscillation. So the light you see scattered from that direction is strongly polarized, vibrating mostly perpendicular to the plane formed by the sun, the scattering point, and your eye. You can see this with polarizing sunglasses.
Wow, okay.
So yeah, we've gone all the way from a single oscillating charge losing energy, this idea of radiation resistance,
To quantifying that loss with dollars to finding the damping lifetime.
using that lifetime to understand why independent light sources just add intensities.
And finally landing on Rayleigh scattering, the omega 4 rule that explains the blue sky and polarization. It's a beautiful chain of reasoning.
It really is. Classical physics explaining something so fundamental and visible.
Well, thank you for joining us on this deep dive. We've seen how Feynman connects the micro world of electron dynamics to the macro world we see every day. And here's something to think about as we close. The whole blue sky argument relied on scattering from individual independent air molecules much smaller than the wavelengths of light. That's what gives the strong omega fourth hour dependence. But as Feynman briefly mentions, what happens when the scattering particles get bigger, like water droplets in a cloud or maybe larger dust particles? Why do clouds look white, not blue? The source hints that interference effects between different parts of the same larger particles start to matter then, washing out the strong color dependence. How does interference, which we just said averages out for independent sources, come back into play when the scatterer itself gets large? Something to ponder.